Welcome back to Bite-Sized Breakthroughs, where we dissect cutting-edge research and bring you the key insights. Today, we're diving deep into a paper that revolutionized the field of reinforcement learning, playing Atari with deep reinforcement learning. Joining me is Dr. Paige Turner, a leading expert in this research area, and Professor Wood Spectrum, whose insights on AI applications will help us understand the broader implications of this work.
Thanks for having me, Alex. It's exciting to discuss this landmark paper.
Absolutely. This paper made a huge splash, but for those who haven't been following closely, could you set the stage, Paige? What were the challenges faced in reinforcement learning before this breakthrough?
Certainly. Before this paper, reinforcement learning (RL) struggled to handle high-dimensional sensory inputs like images or speech. Most successful RL applications relied on handcrafted features, which were designed by experts to capture relevant information from the raw data. But this approach had limitations. These features often lacked generalizability, meaning they were specific to a particular task and couldn't be easily applied to new situations.
So essentially, these systems were very task-specific and couldn't learn on their own from raw data.
Exactly. Deep learning, with its ability to learn hierarchical representations from raw data, offered a promising solution. But there were challenges in applying deep learning to RL. RL problems often involve sparse, noisy, and delayed rewards, meaning the agent doesn't get immediate feedback on its actions. This was a stark contrast to the clear input-output relationships typically found in supervised learning.
And what about the other challenges you mentioned?
Right. Another challenge was the presence of correlated data in RL. The agent's actions influence its subsequent observations, creating dependencies that traditional deep learning algorithms, which assume independent data, struggle with. Additionally, the data distribution changes as the agent learns, which can be problematic for deep learning methods that assume a fixed underlying distribution.
So deep learning seemed like a good fit for RL, but it presented its own set of hurdles. This is where the paper's innovation comes into play. What did they do to tackle these challenges, Paige?
The authors introduced a groundbreaking approach called deep Q-learning, DQN. They used a convolutional neural network, CNN, to estimate the action value function, which essentially tells the agent how much reward it can expect to receive for taking a particular action in a given state. This CNN, trained using a variant of Q-learning, was able to learn directly from raw pixels, eliminating the need for handcrafted features. The key to their success was a technique called experience replay.
Let's break down those terms. First, what exactly is a convolutional neural network? Can you explain it for those who are unfamiliar?
Imagine a network that can detect patterns in images, much like how our brains process visual information. A CNN is designed to handle image data, using layers of filters to extract features like edges, corners, and textures from the image. It progressively builds up more complex representations of the image, leading to a better understanding of its contents.
So essentially, it learns to recognize patterns and objects within the image. Exactly. In this paper, they used a CNN to analyze the raw pixels from Atari games, allowing the agent to learn without any pre-programmed understanding of game elements. Now let's move on to Q-learning. It's a core concept in reinforcement learning, but maybe you could refresh everyone's memory, Paige.
Sure, Q-learning is a model-free reinforcement learning algorithm. It aims to learn a policy or a strategy for maximizing rewards over time. It works by estimating the value of taking a particular action in a given state. This value, called the Q value, represents the expected future reward that the agent can achieve by taking that action and following the optimal policy thereafter. The algorithm uses the Bellman equation, a fundamental concept in dynamic programming, to iteratively update these Q values, aiming to find the optimal strategy that maximizes the total reward.
So it's like the agent learns by trial and error, constantly updating its understanding of the best actions to take based on the rewards it receives.
Precisely. Now, the authors combined this Q-learning algorithm with a convolutional neural network. That's where the deep in deep Q-learning comes in. The network learns to map states to Q values, and it's trained using stochastic gradient descent, which means it updates its weights based on small random samples of data.
So far, so good. We've got a deep learning architecture, processing visual information. and we have Q learning as the foundation for decision making. Now, what is this experience replay that you mentioned, and why is it so important?
Experience replay is a clever technique that addresses the challenges of correlated data and non-stationary distributions in RL. It works by storing past experiences or transitions in a memory buffer. During training, the algorithm randomly samples these past experiences to update the Q network. This random sampling helps break the correlations between consecutive data points, making the learning process more stable and efficient. Additionally, it helps the agent learn from a broader range of situations, preventing it from getting stuck in a local optimum.
That makes sense. It's like the agent is constantly reviewing its past experiences and using them to refine its understanding of the world. So, by combining deep learning with Q learning and experience replay, the authors created a powerful system. Did they have any specific goals in mind for this research?
Their primary goal was to show that a deep learning model could successfully learn control policies directly from raw sensory input in a complex RL environment. They used the Atari 2600 emulator, which provided challenging game scenarios with high-dimensional visual inputs. Their objective was to create a single neural network agent that could learn to play as many of these games as possible, without any prior knowledge about the games themselves.
A very ambitious goal, indeed. Before we dive into the experiments, Professor Spectrum, could you share your insights on the significance of this paper from a broader perspective? What makes this research impactful?
This paper is a pivotal moment in AI history. It demonstrated that deep learning, combined with reinforcement learning, could achieve human-level performance on a complex task like playing Atari games. This was a huge step forward as it showed that AI could learn from experience and adapt to new situations. Previously, AI systems were typically limited to specialized tasks, requiring significant human engineering. This research opened up the possibility of developing general-purpose AI agents that could learn to perform a wide range of tasks.
So this paper was not just about beating Atari games, it was about proving the potential of deep learning in RL for building more general, adaptable AI systems.
Precisely. It laid the groundwork for further advancements in fields like robotics, autonomous vehicles, and healthcare, where AI agents need to operate in complex environments and learn from experience.
That's a fascinating perspective, Professor. Now, Paige, let's get into the details of the experiments. What games did they test their approach on, and how did they measure performance?
They evaluated their DQN agent on 7 popular Atari 2600 games: Beam Rider, Breakout, Enduro, Pong, Qbert, Sequest, and Space Invaders. Each of these games presented different challenges, requiring different strategies. They measured performance using the average total reward the agent accumulated over multiple episodes. A higher reward indicated better performance.
So basically, the agent was given a series of games, and its success was measured by how well it played each one, accumulating rewards along the way.
That's right. They also compared their results to other reinforcement learning methods of the time, such as SARSA and contingency, which relied on handcrafted features. They found that DQN significantly outperformed these methods on all 7 games, demonstrating its ability to learn effectively without prior knowledge about the game mechanics.
That's impressive. Did they also compare their performance to that of a human expert?
Yes, they did. They compared DQN to the performance of a human expert who played the games for a couple of hours. Remarkably, DQN surpassed the human expert's performance on 3 games: Breakout, Enduro, and Pong. It also achieved near-human performance on Beam Rider. These results were truly astonishing, demonstrating the potential of deep reinforcement learning for surpassing human abilities.
So, their deep learning model not only outperformed existing RL methods, but also surpassed human experts on some games. That's a huge leap forward. Did they delve into how their model learned, or did they just focus on performance?
They did delve into understanding the learning process. They visualized the value function, which is the function that the network learns to estimate. They showed how the value function changes over time for a sequence of events in the game Sequest, demonstrating that the network learned to anticipate rewards based on the game's state.
So it was not just a black box. They were able to see how the model was making decisions, which is critical for understanding its strengths and limitations.
Exactly. However, they also acknowledged the limitations of their approach. They noted that DQN could struggle with tasks requiring long term planning or reasoning, as it primarily learned short term dependencies. They also pointed out that DQN is sensitive to hyperparameter tuning, and finding the optimal settings for a specific task can be challenging. They highlighted the importance of future research to address these limitations.
Professor Spectrum, what are your thoughts on those limitations? Do you think they're significant, or are they just part of the expected hurdles in a new research area?
These limitations are certainly worth considering, but they're not necessarily deal breakers. The fact that they achieved such remarkable results, despite these limitations, is a testament to the promise of deep reinforcement learning. These are areas of ongoing research, and we're seeing significant progress in developing more sophisticated algorithms that address these challenges. For example, researchers are exploring methods for incorporating long-term memory and planning into deep RL systems. They're also developing more robust and efficient methods for hyperparameter tuning.
That's reassuring. Despite the limitations, the research clearly opened doors for future progress. What do you see as the most promising future directions for this line of research, Paige?
The future of deep reinforcement learning is incredibly exciting. One key direction is to develop more efficient and scalable algorithms that can handle complex tasks with even larger data sets. Another promising area is to explore alternative architectures and learning methods that can better handle long-term planning and reasoning. Researchers are also working on integrating model-based methods with model-free techniques to improve generalization and planning capabilities. Ultimately, the goal is to develop AI systems that can learn and adapt to a wide range of complex tasks, from controlling robots to developing new therapies in healthcare.
Professor Spectrum, what are some potential applications of this research that you find particularly exciting?
I'm particularly excited about the potential of deep reinforcement learning for robotics. Imagine robots that can learn to perform complex tasks, such as assembly line work or disaster response, simply by observing and interacting with their environment. This could revolutionize manufacturing, construction, and other industries. I also see great potential in healthcare, where AI agents could be trained to assist with diagnosis, treatment planning, and drug discovery.
That's truly impressive, Professor. It seems like this research has the potential to impact our lives in profound ways. Paige, before we wrap up, could you summarize the main takeaways from this paper?
This paper demonstrated that a deep convolutional neural network, trained with a variant of Q-learning and experience replay, can successfully learn to control agents directly from high-dimensional sensory input. It surpassed previous methods and even achieved human-level performance in some cases. This breakthrough is significant because it proves the potential of deep learning for tackling complex control problems, paving the way for further research and development in this field. The impact of this research extends beyond the realm of game playing, offering promising directions for developing intelligent systems that can learn and adapt to a wide range of complex tasks in various domains.
Thank you both for this illuminating conversation. It's clear that this research has had a profound impact on the field of AI, and we're only beginning to see its full potential. We'll be keeping a close eye on the advancements in deep reinforcement learning as this exciting field continues to develop.